We spent last class talking about Kaplan-Meier and the log rank test and variation in the log rank test. I just want to very quickly say something about what we did. Kaplan-Meier is essentially a procedure for figuring out how to plot survivor curves when you're just talking about the crude survival data and you're not trying to control for any variables. We described how you do compute the Kaplan-Meier curve, how it works using this approach called the product limit approach. But for the most part, there's a program in SAS that does it for you, and that's called the life test program. And we showed you some examples of life test, how that works, what the code looks like. And the life test program also allows you to compare survival curves. And the most popular test for comparing two or more survivor curves is called the log rank test. Okay? And we showed you a little bit about what the log rank test does. It's a chi-square test. Its degrees of freedom is the number of curves you're comparing. So if you're comparing two curves, the degrees of freedom is 1. If you're comparing 5 curves, the degrees of freedom is 4. The null hypothesis is that the curves that you're comparing are all essentially the same. They're not significantly different from one another. The alternative hypothesis is that there's some difference between them. And again, it's a chi-square test. And it turns out, again, if it's significant, you conclude that these uncontrolled for, these crude curves are somehow different. That doesn't mean that when you start controlling for things, that the adjusted curves, after you control for other variables, are going to be different or the same. That's another thing you want to figure out and learn how to do that we'll eventually start talking about. It won't be the latter, how to do a test or compare adjusted survivor curves to actually do a test to see that won't be covered for this exam, but it will be something that you'll have to learn for the take-home final, which will primarily be a survival analysis exercise. The other thing about the Kaplan-Meier, the log rank test, is that there are some alternatives. There are some variations on the log rank test, and the sort of the most popular variation that's at least programmed in SAS is called the Wilcoxon test. There's a variation of that called the Peto test. And the Wilcoxon test essentially is a version that allows you to compare survivor curves in which you put more emphasis on the difference between the curves early on during survival. Okay? So that's what the Wilcoxon or the Peto test does. So if you want to emphasize when you're looking to compare curves, which the earlier part of the survivor curve to see if they're different, you use either the Wilcoxon or the Peto test. How you make that decision shouldn't be that you do the test and then you see what you get. You make that decision depending upon what the literature says or what you think conceptually you think is the question of interest. Are you interested in what's happening earlier, or maybe you don't care? You're interested in the entire survivor curve. So that's the key thing about the alternatives. Okay, so that's really all I want to say in review of this, and I want to start talking about the Cox model, unless you have any questions. And again, you've got lab tomorrow to review some of this too. So let's now talk about the Cox model. That's the subject for today. And here we go. It's Cox proportional hazards model. Okay. And there is another form of the Cox model called the extended Cox model that doesn't satisfy this so-called proportional hazards assumption. So we have to talk about what we mean by proportional hazards today. Well, the first thing we're going to do is we're going to look at the formula. We're going to talk about why this model is very popular. We're going to talk about maximum likelihood estimation, because you already know, as I showed you through examples, that the way you estimate the parameters, the betas, or whatever the regression coefficients are in the Cox proportional hazard model, you do it using maximum likelihood estimation. So the way you get estimates of the measure of effective interest, which is a hazard ratio, and getting confidence intervals and do tests are basically the same way as you do tests when you're doing logistic regression, because you're using maximum likelihood estimation. We'll talk about how to compute the hazard ratio, but you already have seen that. You already more or less know that the formula for the hazard ratio is essentially the same formula that we use to get the odds ratio when we're doing logistic regression, except you got a different measure of effect that you're getting. But the formula is the same. It's an e to the beta type of formula. Okay, we're also going to talk about what adjusted survivor curves are, and we're going to look at the program pH-rate, SAST's pH-rate, to talk about how you fit the model and even how to plot survivor curves. So that's the plan for today. I don't know if I'll do it, but that's the plan. So here's the Cox model. That's the first thing we're going to talk about. Okay? What's so funny? You dropped something?
Everything.
Everything?
Yeah.
Oh, okay. Well, all right. Okay. Okay, so here's the Cox model. Now you notice that what's written in this box up here in the top is a formula that has the letter H over here. So what does H stand for? Hazard, right? So what this is a way of writing a model that describes how to do a survival analysis using this Cox proportional hazard model. It's a model defined in terms of the hazard function, not in terms of the survivor function. But remember what I said at least the last two classes is that if you know the hazard or you can estimate the hazard, there's also a mathematical way you can get the survivor curve. There's a mathematical relationship between one and the other. So when you're using this formula or a program to estimate the hazard, the program is also going to allow you to get the survivor curve, which is one of the things you want to get, to see what's going on, how curves compare over time. But you also want to estimate a hazard model, and you also want to be able to estimate hazard ratios, which is what you're trying to get out of a hazard model. So when you're talking about the hazard formula for a Cox model, first of all, you're talking about one of the key variables of interest, one of the key issues of interest in doing survival analysis is time, because the key outcome variable is survival time, how long people survive until they fail. Okay, so when you talk about the hazard function, you have to talk about h of t, and then you have to talk about this x. Now this x, which is written in bold, represents the collection of predictors. We use the same notation when we're talking about the logistic regression model, except I called it P of x. Now I'm calling it HT of x, and this bold x represents the collection of predictors that are going into the model, the variables that you want to use to predict the outcome, and the outcome is survival time. And the predictors, of course, as we did for logistic regression analysis, one of the predictors might be an exposure variable. It typically is. And another predictor or other predictors might be variables you want to control for. And other predictors or other x's might be products of exposure and exposure variable with a variable you want to control for. And if you put a product term in the model, then you're dealing with what? Interaction, right? So the x's could be any one of a bunch of things. So the x's stand for the explanatory of the predictive variables you're interested in studying and interested in putting in your model. Now, if you look at this formula, you notice that there's a sort of two parts to the formula. There's a part to this formula that says h sub 0, h naught of t, and then there's a part of the formula which is an exponential part, e to the sum beta ixi. So the Cox proportional hazard model formula is the product of something which is referred to the h naught of t is called the baseline hazard function, and the other part is called the exponential part of the model, the e to the sum of beta ixi. And this is a key feature of the model that actually has something to do with what the proportional hazard assumption is all about. But let's talk about these two things. First of all, the baseline hazard is written h sub 0 of t, and you notice the way it's written, you don't see any x's there. H sub 0 of t, but there's no x in there. H sub 0, it's not t comma x, it's just t. So this baseline hazard is a function of time, but it's not a function of the x's. It's not a function of the predictors. And you also notice that on the right side of this product, the e exponential part is a part that involves the x's but doesn't involve time. So if you look at this formula, the left part of the product involves time but not the x's, and the right part involves the x's but not time. Okay, that's a key characteristic of this formula. That's what I say over here, x's but not the, although because they involve x's and they don't involve time, actually what you're essentially saying is that you're restricting the x's in this model to be variables that are called time independent. In other words, what you're saying is whatever variable I'm putting in this model that I'm calling an x is a variable that I'm assuming doesn't change over time. That's what you mean by time independent. We're assuming that if one of the variables is race, that variable doesn't change over time. You're either white, black, Hispanic, whatever you are, okay, and that stays fixed. If you're talking about a variable sex, doesn't change over time. Talking about smoking status, you're assuming that you're doing a study that you're not allowing smoking status to change over time. You're measuring it once, and once you measure it, you're assuming that's what it is, fixed during the time of the study. Another variable that you might start worrying about there is what about age? Well, we know age changes over time, right? So if the study is going on for 3 years and you know the age of people when the study started, you know after 3 years they're going to be, if they're still in the study and they haven't failed, so to speak, they're going to be 3 years older. So that variable inherently is a time-dependent variable. But when you're doing the Cox model, what you sort of do is you essentially say, well, if I want to treat this variable as a time-independent variable, what I'm saying is that even though age changes during the study, as far as I'm concerned, knowing the age at the beginning of the study is the only important thing I need to know about age. It doesn't matter whether the study isn't long enough for the amount in which age changes is going to affect the outcome. So we're treating essentially the age at the start of the study as being fixed. And even though the person actually changes in their age, we're treating it as it's time independent because we're not worried about how it changes. So we're talking about so what I'm saying is the X in a Cox proportional, the X's in a Cox proportional hazards model are assumed fixed, even though in fact inherently they might be time dependent. Okay, so now if you've got a situation where you do want to deal with a variable that does change over time, you can do that and do a survival analysis that way, but then the model is no longer the Cox proportional hazards model. It's an extended version of it. So I call it the extended Cox model, and the proportional hazards assumption, you notice at the bottom of the screen I say no pH. That's not satisfied when you're dealing with a model that has time-dependent variables. But we're not going to get to that for a couple of weeks. We'll not get to that until after the second midterm. So we're not going to worry about that until later. So we're going to be assuming everything's time-independent. So that's the model. And here's what I say. Time-independent variable values for a given individual do not change over time. Time-dependent variable and x whose values for a given individual can vary with time t and requires an extended Cox model, which doesn't satisfy the pH assumption. Okay. Now it could be, again, as I said, age might be, even though it changes, you might consider only knowing the age at the start of the study, when somebody enters the study, is all you need to do to be able to do a good analysis, and then you're assuming age is time independent. If you don't want to assume that, then you're actually going to wind up having to do an extended Cox model, which is a little bit more complicated, or it's just an extension. Okay, so now we had examples, when I originally introduced the Cox model, examples of this remission time data, where you had two groups of people, 21 in each group. They all had leukemia, they all were in remission. They were originally leukemia patients that were in remission, and they were being followed over time, over a certain number of weeks, to see whether they went out of remission. And there were two key variables that we looked at. One was, and there's a third variable that I think I added when I talked about the life test program and how you get Kaplan-Meier curves, variable sex. But the two variables we're looking at right now is whether somebody is in a placebo group or a treatment group, and the other variables if ever we want to control for, which was log white blood cell count. Could have been white blood cell count, but the investigators felt that log white blood cell count was a better predictor, so that's the way they chose to use the predictor. That's the way they chose to define this variable. Now you notice this variable is defined 1 of placebo and 0 of treatment. Why do you think, I think I have talked about that before, why do you think it was defined this way and not 1 of treatment, 0 of placebo? It could have been done that way. Why was it done that way? Because if you remember when you looked at the original crude data, the hazard ratio was like 4.6. But that hazard ratio, 4.6, is what you get when you divide the hazard for the placebo group over the hazard for the treatment group. And you get a number larger than 1. And if you define the treatment variable this way and you run a Cox proportional hazard model, you're going to get, because of the way the data is set up in this particular example, you're going to get a hazard ratio estimate that's going to be larger than 1. And the only reason why you like that is because it's easy to interpret. It's easier to interpret a 4.6 than a 0.373 or something like that, if that's the hazard ratio, less than 1. So that's the reason why we often define our exposure variable in a way so that we can get a hazard ratio that's easier to interpret, even though we could always define it the other way. So now what I've done is I've written on this slide 3 models, and these were the models that I showed you the output for when we first started talking about survival analysis and when we first started looking at the remission. But these are the 3 models. The first model just had the treatment variable in there. The second model had the treatment variable and log white blood cell count in there, and the third model had treatment, log white blood cell count, and the product of treatment and log white blood cell count. And these were the 3 models we looked at. And if you remember, when we looked at model 3 and we looked at the output, we found that the product term, the interaction, wasn't significant, right? So we could drop model 3. And when we looked at model 2 and compared it with model 1, it looks like there was a 10% change in the measure of effect. What's the measure of effect? Hazard ratio. And in order to see the change, whether there's a change, we look at the hazard ratio for model 2 and the hazard ratio for model 1 and see if they're 10% different. And if they are, then we say, well, if they are 10% different, then we say, well, we can't drop log white blood cell count, and model 2 would be our choice, our best model. And this is what we do if we're doing a survival analysis, but it's the same idea, modeling strategy, that we talked about when we're doing logistic regression in this very sort of simple example. So that's what these models look like, and as you can see, these 3 models are in that general form that we've written over here, because baseline hazard times an exponential part, and there's the baseline hazard on the left side of each one of these models, and there's the exponential part. The exponential part has 1 variable here, 2 variables here, and 3 variables here. So that's what a model looks like. That's what a Cox model looks like. Big deal. It's really not that complicated. Okay, now, one thing to say about this model has to do with this thing called the baseline hazard function, because it's sort of a weird type of function. It's a function of time, doesn't involve the x's, and it's a function that's left unspecified. Other than saying it's a function of time, you don't have to write, when you write this model, you don't write any particular model formula for the function. For example, you don't write h naught of t equal t squared. You don't say what that function, you just leave it as an undefined function of time. Okay? And in other words, there's a part of the model that's left undefined. There's a part of the model that's defined, that is the mathematical part of the model, and that's the exponential part. But this part of the model is left undefined. And that's why this model is often referred to as a semi-parametric model. So what's a parametric model? This is a semi-parametric model. A parametric model will be a model where everything is mathematically determined. So if for example, if h naught of t was equal to 1, if the baseline hazard was just a constant and was equal to the number 1, then we completely know the mathematical form of this model. Everything would be determined. And we wouldn't know what the estimate of the betas were, but we know the general form of the model, the mathematical form of the model. Okay? If it turned out that the model was, so what do we mean by a non-parametric model? What's a non-parametric model? Something where there's no part of the model that's specified. We don't know what it looks like. And we don't have any general form for it. So this is a semi-parametric model. The baseline hazard is left unspecified. That's why it's an example of a parametric model is one, as I said, if h naught of t was 1, then this model would just be e to the sum beta ixi, and this would be an example of a parametric model because the model is completely determined. So I'm just repeating what I just said. Okay, now here's another example of a parametric model. Parametric model, where h naught of t is not 1, but it's some function of time. Alpha, where alpha is some number, some constant, could be alpha, could be 3. T to the alpha minus 1. So in other words, there's a formula for h naught of t. And if there is a formula for h naught of t, and then you write it together with the exponential part, then you're talking about a parametric model. And this particular form of the baseline hazard makes this model, it's called the Weibull model. It has a certain general parametric form. It has a certain, if you try to graph what the hazard function looks like, it has a certain form, as opposed to some other kind, as opposed to an exponential. Weibull and exponential are not the same thing. But in any case, there's a lot of different kinds of parametric models that you can get if you specify the baseline hazard function. And the Cox model doesn't have it specified. Okay, semi-parametric. So then the question is, okay, well, we can have parametric models and non-parametric. Which one do we want to use? Well, it turns out, as I say over here, the Cox proportional hazard model is very popular because it has this property of robustness. And what that essentially means is that it usually gives good results regardless of what the correct parametric model is. In other words, if you don't know or don't want to take a guess at what the baseline hazard function looks like, or you don't want to be able to say that the true parametric model is Weibull, or it's exponential, or it's something else, and you decide to fit a Cox proportional hazards model to the data, you typically do a good job of getting what you want to get. You get a survival curve, you get a hazard ratio, you get confidence intervals around it, you get a test of hypothesis. Typically does a good job to do that. So that's why it's popular, because it typically does a good job. In fact, see, one of the things you should be worried about, you could be worried about, is if you choose a baseline hazard function, say, well, I'm going to fit a Weibull function to it. For some reason, you figure out that's what I'm going to do. Well, what if it's truly not Weibull? What if that's the wrong choice? Then you might get bad answers in terms of your survival curve, your hazard ratio, and so on. So you're sort of taking a chance to do a parametric model, a certain specific one, that you're not necessarily taking when you're doing the Cox proportional hazard model. Of course, if you have good reason to choose a model like the Weibull model, and there are various ways to do that. What's one reason why you might want to choose a Weibull model? You can think something up if you had to free associate some answer. It might be simply that from the literature, whatever you've been studying, always, the outcome that you've been studying always turned out to be Weibull when they actually looked at the data. And so it may make sense for you to consider your study, because it relates to something that previously been studied, as a Weibull model. It's also possible there are ways you can graph survivor curves or even graph hazard functions and use sort of plots to actually determine whether it looks like from your actual data, whether you can say it looks like there's a particular parametric model or function that fits. You remember, you may have learned this in your first biostatistics course, if you wanted to see something that was normally distributed, there was something called, did you ever hear about normal probability plots? Did you? Not sure if you did. There's a way, and there are computer programs that will allow you to plot the cumulative distribution of your data, and if you look at it, it looks like it's on a certain graph, and if it looks like it's about a straight line, you can say the data is approximately normally distributed. Now, there are similar kinds of things you can do with plots to see whether the data is approximately Weibull, approximately something else. So that's what sometimes people do if they want to consider a parametric model. But you're taking a chance, because if you choose the wrong parametric model, you could get a bad answer. If you choose the Cox proportional hazards model, you might generally get a good answer regardless of what you might choose for the baseline hazard. So that's what I want to say about robustness. That's why it's popular. How do you estimate the parameters in a Cox report? I've already said this. You use maximum likelihood estimation. And what you do is, just like we talked about when you do logistic regression, there's this thing called the likelihood function. It's a mathematical function. It's a mathematical function of the data and the model, which contains these unknown parameters. And it's a mathematical expression that contains that reflects the data, the variables in the data, and the parameters. And so we often called it L, and sometimes we called it L of B, because L stands for likelihood. Likelihood is another way of saying probability. So a likelihood function is the probability of the data that you got as a function. That's why the beta's in as a function of the unknown parameters. And this beta with a little tilde underneath it represents a collection, not just a single beta necessarily, a collection of the parameters that are in your model. You might have a beta 1, a beta 2, a beta 3, and this beta with the tilde, with the little squiggle underneath it, represents the collection of betas. And so the likelihood function is some mathematical function that gets maximized. And the betas that you choose, that you find that maximize this, are considered the maximum likelihood. They're sort of the most probable estimates that you can fit given the data that you got and given the model that you have. Now, again, you don't ever have to do this. It's a complicated formula. It's built into the computer program that you use. The computer program is PH-RAY, and you can get the program to give you the estimates without ever seeing what this likelihood formula is. Now, I will say something is, the formula, I'm going to say a few things even though you don't really care about the details of this thing. The formula is called, actually it's called a partial likelihood, because what it does is, it's based on, remember how I took the data and I had two different data layouts, and one of the data layouts I had to order the times at which people failed? And in order to do that, I had to look and see, okay, who failed? What are the failures? I also had to see who was censored in order to set up that second table that I showed you. Well, it turns out the partial likelihood is based on an expression that is formed only involving the people that fail. Only involve the people that fail. The people that are censored are considered in the formula, but not directly it's not directly calculated. It's calculated in terms of, when you go from one reset to the next reset, you lose people who are censored. So somehow it's reflected in this formula, but it's not reflected in the way that the formula really is defined in terms of the ordered failure times. So it doesn't consider the probability of the subjects who were censored. In other words, it only consider the ones who have failed. And in fact, you can write the likelihood function as the product of a bunch of sub-likelihoods, you might say, where each of these likelihoods represent the number of the K represents the number of failure times. So L1 is the likelihood for the first time that somebody fails, and L2 is the likelihood for the second time that somebody fails. What allows you to write the product? What allows you to write the product? Remember the product of A and B is, if you ask the old probability of A and B was the product of probabilities. So what are you sort of assuming here? Well, what you're assuming here, it's not exactly independent. What you're assuming is L1 is based on the first time that somebody fails, and L2 is based on those people that failed, given that those people that failed after the first time, given that these are the ones that are left over. In other words, L2 is determined from the risk set, only those people that are left over after you get rid of the people that failed at time one. So in some sense, this is a conditional probability. So it's P of A, P of B given A, P of C given A and B, and so on. So that's what allows the product. They're independent given that it's conditional, but that's just a mathematical. The main thing is that there's a program, PH-RAY, there's a formula, and it maximizes it, and it uses the subjects who fail, only the subjects who fail to actually get the formula. And the way it does it, as I think Eli talked about, and maybe I talked about it last semester when I talked about logistic regression, it tries to maximize the likelihood, because that's the whole idea. But the way it maximizes the likelihood, it actually maximizes the log of the likelihood. And the reason is that the likelihood formula is a product of a bunch of things. And if you take the log of a product, it's the sum, the log of a product is the sum of log. And it's easy that when you maximize something, you're talking about calculus, talking about taking a derivative and setting it equal to 0, if you may or may not remember that. But when you do that, it's much easier to take derivatives when you're adding the derivative of a sum as opposed to the derivative of a product. So what you do is you take a derivative of this log likelihood function and you solve for the unknown parameters, and it's solved on the computer using what's called iteration by guessing at a solution and eventually coming to an answer, and then you use that answer. So, okay, so that's how it works for what it's worth, and you're going to from now on, and you know, even if I didn't say this, you're going to just use the computer to do this. Now, the next issue is, okay, there's this model. There are these parameters in the model. It's fit using maximum likelihood. We know how to do maximum likelihood estimation, whether we're dealing with hazard ratios or odds ratios. But what about the hazard ratio formula for this model? What does it look like? Okay. And the way it was described when we're talking about logistic regression, we talk about, well, let's talk about two individuals, individual X star and individual X. Individual X star might be exposed and have certain values and variables you want to control. Individual X might be unexposed. I mean, they may have different values for the different X's. Maybe they have the same values on the other X's, but they only differ on the first value, on the first variable. But in any case, the formula for the hazard ratio is simply, again, as defined, is the hazard for person X star divided by the hazard for person X. And it turns out that formula looks like this. And then you've seen this formula before, because this is exactly the same formula that we had when we were using logistic regression. It's exactly the same formula. Why does this work? Why does this work? Well, if you think about it, and I didn't do it on this slide, but the reason why it works, if we go back to the original formula, if you've got an expression like this for X star, and an expression like this for person X, and H naught of t doesn't depend upon X, and you're dividing one thing by another with the same H naught t in the numerator and denominator, they're going to cancel out. So you never have to have H naught t in the expression for the hazard ratio. So that's why the hazard ratio is written like this. Okay? So if it turns out, for example, the first variable is 1 if you're X star and 0 if you're X, and all the other X's are the same, for they don't change from one person to the other, then the hazard ratio would be beta 1 times 1 minus 0 plus beta 2 times the same difference between the same thing. These things would cancel out, and you get e to the beta 1, which is the same old thing. And the way you compute the hazard ratio, if there's interaction or other variables in the model that you're controlling for, is an exponential formula where this is the general expression for it. So this is a piece of cake in terms of doing it. So for example, in the remission time data, where the model, if we're just focusing on model 2, which we sort of decided was the best model, and only had treatment and log white blood cell count in the model, and that was the general formula, when you wind up fitting the model, you wind up getting the coefficients of treatment and log white blood cell count. Again, the treatment variable is defined as 1 of placebo, 0 of treatment, and the coefficients, the two estimated betas, are 1.294 and 1.604. And if you want the hazard ratio for the effective treatment adjusted for log white blood cell count, then it would be beta 1 hat x1 star minus x1, which is 1 minus 0, and x2 star minus x2 is if you're controlling for log white blood cell and you're keeping it the same, this part of it would cancel out, so you just get e to the 1.294, which is e to the, that's the answer, and whatever that is, and there it is, 3.648. That's the number we saw last time when I showed you that. That's the hazard ratio for the effective treatment adjusted for log white blood cell count in this model. So it's really easy to do. And then if you have a more complicated model, which we didn't need to have. You remember, model 3 we didn't really drop because we didn't have a significant interaction. But if we decided we wanted to play around with model 3 and just see what the hazard ratio formula would look like, whether model 3 was appropriate or not, we now have 3 variables, log white blood cell treatment and the product term. And so that means that the formula, again, the formula is e to the sum, beta I hat, and the corresponding difference between predictive variables. So it's 2.355 is the coefficient of the treatment variable times 1 minus 0, because those are the placebo minus treatment. And then it's 1.803 times the log white blood cell count minus itself, because you're fixing that. And then it's minus 0.342 times the difference between these two terms. And one of them is the product 1 times log white blood cell count, and the other is the product 0 times log white blood cell count. And this doesn't drop out. You wind up just getting log white blood cell count, and that's the formula for the hazard ratio in this model. So it's not e to the 2.355. It involves the formula involves whatever the value of log white blood cell count is. And depending upon what it is, I've plugged in values 2 and 4, I'll get different values for the hazard ratio. If the log white blood cell count is 2, hazard ratio will be 5.32. If it's 4, it would be 2.68. That's what you mean by interaction. So if there's interaction, you're going to get different values for the hazard ratio. Anyhow, so that's how you get the hazard ratio. What did I drop? Not sure, but okay. And this is another way to write the formula for the if we have 0, 1 exposure variables, and you have product terms in the model, and the general formula is it's e to the beta, where beta is the coefficient of the exposure variable, plus the sum of the delta w's. This is like the EVW way of writing the model, where the deltas are the coefficients of the product terms that involve E with whatever the effect modifiers are. And you've seen this formula before. And so in the model where I had the variable E times log white blood cell count in addition to E and log white blood cell count, the hazard ratio formula was E to the beta plus the sum of the delta. There's only one W here, and so I wound up getting the same expression I just showed you here. So it's really the same formula. So I don't think I have to belabor it. You should be very comfortable with this formula now. So what's this? What am I showing you now? This shows you how you use the program PH-REG to run a Cox proportional hazards model. Okay, that's what it says. Okay, so you have to put the name of the data set in, you have to put the variables that you're using. You want to have a product term, and it's not in the original list, you have to define it. Usually you write data lines instead of cards, but the computer can read this too. You put the data in, you say run, and then you write as many statements as you want to write that describe the model. Apparently a P dropped out over here. This would have been proc, disappeared. But in any case, if you look at each one of these models, let's look at the second model, which is model 2. You notice it says it's got model, and it's got serve T star status 0. So what's going on here? This is what we had to do when we're using life tests, because you remember, when you're doing a survival analysis, you have to tell the computer two things. You have to tell it the survival time, and you have to tell it whether somebody failed or was censored. So you have to give both that information, and the way you do it when you're running either survival life test or PH-REG is you write serve T star. This doesn't mean you're multiplying them. It's just telling them that these are the two things you have to do. When you write it this way, the computer knows these are the two things you're giving it for survival time and failure status. And the 0 represents what? What is the 0? It's the value of the failure status variable for somebody that was censored. So if it turns out the way you coded censored people was not 0 but 5, you put in a 5. That's what the value this is. Okay. And then you write what the variables are. And if you want to see confidence limits, you write RF /RF, and you run it. Okay. And if you do that, for example, for Model 2, you've already seen this output. I showed you this output a few days ago, a few classes ago. This is the output you get This has the for Model 2, it has the two variables in there. It has the parameter estimates. It's got their standard error chi-square, probability of chi-square, hazard ratio 3.648, and confidence limits. And this is what you get when you write that code that I showed you over here for Model 2. Okay. And you notice it also gives you some other information. And the key bit of information here that, as far as we know up to this point, that you want to use is the minus 2 log L. What do you use that for? What's minus 2 log L used for? You want to do a likelihood ratio test. So suppose you want to do a likelihood ratio test that tests for whether there's a significant effective treatment status. What do you have to do? This is survival analysis in concrete. What would you have to do? You'd have to fit how many models? Do a likelihood ratio test. 2 models. This is one of them. And what other model? You have to drop a variable. Which one would you drop? The null hypothesis is that the coefficient of the treatment variable is 0, so you drop the treatment variable. So you'd run a model which has just log White-Bledsoe count in the model. You look at minus 2 log L for, now, you see it says without covariates and with covariates. Which one do you look at? The with covariates. You look at for this model, the full model, and you look at it for the reduced model. Without covariates or with covariates? For the reduced model. It would also be with covariates, because there is a covariate in the reduced model. It's log White-Bledsoe count. You don't ignore covariates. So you'd have to get the 2 minus 2 log L, subtract one from the other, and it's a chi-square with how many degrees of freedom? 1, just like we did when we did logistic regression likelihood ratio test. Now, what about the Wald test? Is that shown here? Yeah, it's the same thing. The Wald test is given right, the Wald statistic is 23.7318, and it's highly, that's for the log White-Bledsoe, which we're not interested in. For the treatment variable, it's 0.0022, highly significant. Okay. So we're not really interested in this. We want to control for it, but we really don't care necessarily. We would hope that it's significant, because the reason why we control for it is because we thought it was an important predictor of the outcome. So we would sort of expect it to be significant. But the main thing is looking at the treatment variable. So we're moving our way through this, and it's not that hard. Now, what's this? Well, this is something I'm going to show you how to do it before we quit today. This is edited output using PHREG of adjusted survival curves for Model 2 of the remission data. That's what this picture says. Okay. Now, do you remember me showing you what the Kaplan-Meier curves for the remission, for comparing the two curves, comparing treatment and placebo? I don't know if you remember it exactly, but we saw it just one class ago. They were very similar. Early on, they weren't that much different, and later on, they were different. They were much more different. So this is comparing one group with the other, and the group that's higher is the treatment group, because that does better. The treatment group had better survival probability, if you remember that. But in any case, these are not Kaplan-Meier curves. These are what are called adjusted survival curves. In other words, you originally started with Kaplan-Meier curves, but now you're comparing these two groups, treatment and placebo, but now you're doing it within a model that you have another variable that you put in the model, log White-Bledsoe count. So it turns out that in this case, this picture looks very similar to the picture that we got when we did unadjusted Kaplan-Meier curves. Kaplan-Meier curves are unadjusted. These are adjusted. Now, they don't necessarily will always be the same. They won't necessarily, and this isn't exactly the same, but they don't necessarily often look even that similar. They could be very different when you start adjusting for variables. But it doesn't seem to make much of a difference. So it looks like when we just consider treatment and log White-Bledsoe count, it looks like we're getting the same picture, that the treatment group does better. Okay. So that's another thing that we see. Okay. Now, I'm not going to spend time on this, but you can run this, you could do survival analysis using Cox model, using Stata, and you can do it using, you can even get plots using Stata, and you can also do it using SPSS, and you can also do it using R, which is now popular because it's free. So, but anyhow, that's it. So the next thing I want to talk about is Well, this whole business, what do we mean by proportional hazards? What's that assumption? What does that have to do with? Okay. So to talk about that, just remember we already saw that the formula for the hazard ratio, comparing x star with x, was this, right? E to the sum, beta j, xj star minus xj, where j, the xj was the jth variable. Okay, that's the formula. Now, one thing you notice about this formula that I didn't really point out exactly before is you notice that in the model, remember the exponential part of the model had variables that were time independent. They weren't dependent upon time. They were x's, but they weren't x's that varied with time. So you notice that in this expression, this is an expression that doesn't depend upon time. It only depends upon the difference in the x's. So e to the sum beta j xj star minus xj gives you a number. I'm referring to this number sort of generally as a theta or theta hat. It's an estimate, okay? But it's not a number that varies over time because there's nothing involving time in this expression. So it's an expression that doesn't involve time. In fact, you notice this is a formula for the hazard ratio. And what you're essentially saying is that the hazard ratio, comparing one person with another person's hazard over time, doesn't depend upon time. So if we considered a plot where we had time as the x-axis and hazard ratio estimate on the y-axis, then the hazard ratio would only depend upon what the difference was between x star and x, how those two people differed on the x's, but it had nothing to do with time, and that's why you see this horizontal line. That means the hazard ratio is constant over time. Isn't that what that says? It says the hazard ratio is constant over time. So that's one way you could say that's what the proportional hazards assumption means. That if you're using a proportional hazards model, you're dealing with a model so that the hazard ratio comparing any two individuals, any two x's, any two different people, hazard ratio is going to be constant over time. It's not going to vary over time. Okay. Another way of saying that is that if this hazard divided by this hazard is equal to this number that doesn't depend upon time, then I can write ht of x star as equal to theta hat times x of t. If a over b is equal to c, then a is equal to b times c. Just simple algebra. Okay? And this is another way of saying that you can get one hazard from the other hazard by only multiplying it by some number that has nothing to do with time. And that's why theta hat here is often referred to as a proportionality constant. And that's why people say this is why it's called the proportional hazard model, because one hazard is proportional to the other hazard in terms of you can get one hazard from the other by some multiplying it, and you don't have to worry about time. That's what this says. So these are two ways to say. One way to say is the hazard ratio is constant. The other way is to say you get one hazard from the other by multiplying one of them by some constant that doesn't depend upon time. Only depends upon the x star and the x's. It'll be different depending upon the x star and x's. Okay. Now, you notice that I said down at the bottom, I said, well, if the hazards cross, then the proportional hazard assumption can't be met. So look at this picture. Isn't this picture, now look at this picture. Is this a graph of hazard ratios? The one at the bottom. This picture at the bottom. It's actually not a graph of hazard ratio. It's looking at two groups, group A and group B. And it's plotting the hazard function, assuming that I knew what the hazard function was. I'm just sort of taking two hazard functions that I'm sort of dreaming up. And I'm plotting these two hazard functions, one for group A, one for group B. And when I plot them, you notice they intersect, right? They intersect. Okay. Now, if they intersect, what can you say about the hazard ratio comparing group A with group B? Is it constant over time? And you know it's not because, for example, before the intersection, the hazard ratio comparing A to B is larger than 1, right? Because the hazard ratio for A, the hazard for A is larger than the hazard for B, right? At this point, the hazard ratio is 1. At this point, the hazard ratio for B, the hazard for B is larger than the hazard for A. So the hazard ratio of A to B is a number less than 1. So if this was the case, if this was the situation, then it wouldn't be appropriate to use a Cox proportional hazards model because the assumption's not satisfied. Okay, so there are situations where you can't use the Cox proportional hazard. This is an example. Okay, this is not a great example. I'm just picking this up in the air, but here's sort of a more natural example. You're talking about cancer patients. And when you have cancer, there are different ways to treat them. Some people undergo surgery. Some people get radiation without surgery. Some people get both. Well, let's talk about you've got patients, some of which get surgery, some of which get radiation without surgery. And the key question of interest is if the people who get surgery, do they do better? Do they survive longer than the people who got radiation without surgery, or vice versa? Okay. Now, what I'm saying is, if this was the situation, is this model appropriate? Can I actually just put, now I'm not even controlling for any other variable, I'm just putting in the variable E, where E is a 0-1 variable, 1 if no surgery, 0 if surgery. Okay. Now, you know, the problem is that you notice that if you're dealing with a serious illness and you're having major surgery, serious surgery, then once you get the surgery, you have to recover from the surgery. So even if the surgery helps you to get better, you still have to get through the recovery process. Okay? So you're at risk for something else, or you're at risk for dying. If the outcome is death, you're at risk for dying or at risk for some more serious response or outcome early on after you get surgery compared to people who didn't get surgery. Okay? So that's why the answer to this is no, because the pH assumption is not likely to be satisfied. Now, just to give you an example, here's the picture. Here's the picture of what this sort of says. Look at this picture. What have I done? I've sort of hypothesized more or less what the hazard functions more or less look like without having any specific data. But you notice that E equal to 1 stands for the surgery, E equal to 1 stands for the no surgery patient, and E equal to 0 stands for the surgery patient. Okay. And what do you notice about the hazard? Well, you notice again they cross. So if you're talking about, and they cross, let's assume it takes 3 days to get over the surgery. Okay. So at 2 days, if you have, now this is the no surgery patients versus the surgery. At 2 days, if you have no surgery, well, if you're talking about the hazard ratio for surgery over no surgery, it's less than 1. Did you see that it's less than 1? Because the no surgery is higher than the surgery. So the hazard ratio at 2 days is less than 1. But the hazard ratio at 5 days, after you got over the surgery, is greater than 1. So this would not be a situation where you could use the Cox proportional hazards model. And so clearly, if the hazards cross, the Cox proportional hazard model is not appropriate. Now, it also turns out if the hazards don't cross, it doesn't automatically mean the pH assumption is satisfied. The key is that there's some things we have to get at as we're talking about. How do you check the proportional hazard assumption? But this is so now, what might you want to know if you saw this? If you had this situation, what would you want to know? You said, well, you might say, well, gee, I can't use the Cox proportional hazard model. Well, I'll just give up. I'll quit. I'm not going to study survival analysis anymore. Or the other thing is, maybe there's another way I can do it. Okay. So what else could I do? Well, there's a number of things you could do. One thing you could do is you could say, well, look, and I got it on the next slide here. I got a bunch of things. One thing you could do is, well, I'd say stratify by exposure. One thing you could do is to simply say, look, I'm just going to look at the survivor curve for the surgery patients and the survivor curves for the non-surgery phase, and I'm not going to fit a Cox proportional hazards model. I'm just going to get Kaplan-Meier curve. I'm not going to fit it. I'm just going to look at the curves separately by exposure if I'm not controlling for any other variable. So that's one thing I could do. Another thing, I don't know if I had it on the next slide. Another thing I can do is say, well, look, let's wait until people get over surgery and let's see what happens. But let's wait 3 or 4 or 5 days and then let's compare the curves. So we're not going to use the data prior. That's another thing you could do. And that way, it may turn out you could say that I can use a Cox proportional hazards model after surgery, after they get over surgery. There's a problem with that this picture sort of says. Suppose I start at time 3. And I say I'm not going to look at the data until time 3. And suppose this was actually the picture. What does the picture say about, is the hazard ratio constant over time? Does the picture say that? This is always higher. No surgery hazard is always higher than the surgery hazard, which is good for the surgery. If this is higher than that, it's good for the surgery. Surgery's doing better. The hazard for the surgery is better, less. Okay. But what does this say as you go from here outwards? What's going on with the hazard ratio? Is it constant? No. It's changing. It's just getting bigger. Okay. So you could try to start at 3 and do like this, but you still might have a problem where the hazard ratio isn't constant. So there are other options. So as I say, start the analysis in 3 days. That was my second thing. Another thing that you could do, and we're going to be talking about this, is you can say, well, let's fit the Cox model before 3 days, and let's fit the Cox model after 3 days. And so we know things change after 3 days, before and afterwards, but let's assume maybe before 3 days, well, there's a difference, but maybe there's not that much of a difference. There is a difference, and maybe there's a difference after, but not that much of a difference. So let's do before and afterwards. And that's one thing we can do. And if we do that, approximately before 3 days, and that we have to assume that the hazard ratios before 3 days and after 3 days separately are constant, which may not be appropriate. But if we do that, effectively what we're doing is we're assuming that the hazard ratio, there's an interaction with time. Hazard ratio varies with time. So it almost says that somehow we need to put something in the model that reflects interaction. And that's what actually you're doing when you're using an extended Cox model. So if you actually do this, you're doing an extended Cox model. We're not going to talk about it until a couple of weeks, but I'm just saying that's another thing you can do. Another thing you could do is actually, this is where we're talking about the interaction. You're saying that exposure varies with time. The effect of exposure varies with time. Before 3 days, it's one thing. After 3 days, it's another. Why don't you put in a variable E times time in the model rather than putting E in the model by itself? Well, when you're doing that and you're putting a variable E times time in the model, what kind of a variable is this? Is it a time-independent variable? No, it's time-dependent. So what are you doing? You're no longer using a Cox proportional hazards model, you're using a different model called the extended Cox model. So we're going to learn how to do this, but I'm just saying, if the proportional hazard assumption is not satisfied, there are things you can do. And in this example, there are a number of different ways you can do it, but one of the ways is to fit an extended Cox model. Okay, so, done with that. Now, a couple more things to do here. Okay. Now, we've talked about the model, we've talked about the hazard functions of the model, and we want to get the hazard function and fit the hazard function because if we have an exposure variable, we want to get a hazard ratio. We want to see what it is, we want to test for it, whether it's significant, we want to get a confidence interval around it. But another thing we also want to get is a survival curve, because the survival curve does something more than what a hazard ratio does. The survival curve tells you what's going on over the entire period that you're studying, where the hazard ratio is a summary measure for the entire, but not telling you what's going on at one time compared to another. So we also want to estimate the survivor curve. Okay, that's what we want to estimate, the survivor curve. Now, in order to do that, we have to recognize that, first of all, the model that we used to get all this was the model that was stated like this, HT of x equals this. That was the model that was used to get the hazard ratio. It was fitted and all of that. That was the model that was used. Okay. Now, in order to get a survivor curve, we have to rewrite the model. We have to change what we're doing to get a survivor curve by writing the model in the survivor function form of the model. And there's a way we can do that because why? Why is there a way we can do that? Because there's a mathematical way to go from the hazard function to the survivor function. That's why we can do that. So all I've done here is to say, well, I can go from here to here. The thing I'm going to call that corresponds to the baseline, not the baseline, to the main hazard function, is the survivor curve at time t for a person with a set of predictors x. And corresponding to the baseline hazard function, there's something called the baseline survivor function. If I know the baseline hazard function, there ought to be a way I can get, even though it's undefined, there ought to be a way, integration. You remember how you go from the hazard function to the survivor by taking an integral, even though, it's not clear how you do that or whatever it is, but you can get one from the other, so that's the baseline survivor function. And if you do this, it turns out that the way you have to write the survivor curve, it's not h naught of t times this is s naught of t raised to the power e to the sum beta ixi. So this is an exponent of the baseline survivor curve. So that's the survivor function formula for the hazard model. Now we're not done yet because that's the general formula. Now if you have data and you have a program that fits the hazard function, the program is going to give you estimates of the betas. So you can get beta hats. Okay? It also turns out, believe it or not, even though the baseline hazard isn't specified, there's a way you can actually, the computer, and there's a mathematical formula, but it's complicated, that you can actually estimate the baseline hazard function, even though it's not specified. You can estimate that using the data, and then convert it to its survival form equivalent, the baseline survivor curve. Okay, so you can actually get an expression for this. So in other words, you can get an estimate, there's an expression for an estimated survivor curve that's a function of the estimated baseline survivor and the estimates of the betas. So if you want to get a survivor function, if you want to actually get a survivor curve, and this says st of x, and this is a number that depends upon time, right? It's s naught of t hat of t, and this is a number that doesn't depend upon time. So if I wanted to get survival probability, for example, at time 0, suppose I wanted to get we know what the answer is. What's the survivor curve at time 0? Always, doesn't matter what we're dealing with. It's 1, right? So if I plug in 1 over here, what's s naught hat of t, where t is 0? It's always 1. It doesn't matter whether you're dealing with baseline or any survivor curve, it's always 1. And it's going to be 1 raised to whatever this is. What's 1 raised to anything? 1 raised to the 10. 1. Okay? So the baseline survivor thing is going to be 1. Now if I take any other time, I plugged in 0 here. If I take any other time, like 3 weeks, and I plug it into this expression, or I let the computer compute it for me, I don't have to worry about 3 weeks here, because there's no time here. I can get the computer to compute the survivor probability at 3 weeks by working into what this expression is. And I can get a number for what the survival probability is at 3 weeks. And I can get a number for any other time. And so this formula allows me to get a survivor curve by plugging in different values for t. Now, for example, again, here's the remission time. This is the model 2. Okay? So that's the formula for the hazard function for model 2. We already saw it. This is the formula for the survivor, the corresponding survivor curve for model 2. I haven't written an expression for this, but this is what it would be if that's the baseline hazard, and it's e to the 1.294 rx plus 1.604 times log y plus that. So to obtain a survivor curve, in order to do that, well, we're not going to get a survivor curve unless we plug in values for the predictive variables. I didn't say this before. I mean, I'm really not going to get a number until I put in something for x. So if I put in, for example, 1 for treatment, that means it's placebo. Remember, placebo got 1 and treatment got 0. Plug in 1, and I plug in some other number for log Whitefoot's count, 2.93. I'll tell you why I chose it in a second, but if I plug that number in, and then I compute e to the 1.294 times 1 plus that, I get This exponent is 400.9. That's what the exponent is. Whatever that, okay. And then that means the survivor function is this, whatever this value is, that's going to change as t goes from 0 to 1 to 2 to 3, raised to the power of 400.9. Now you notice it's raised to the power of 400.9, so you might say, ooh, wait, how can this happen? How it's going to be larger than 1? Well, what happens if t equals 0? What's S naught of 0 raised to the power of 400.9? What is it? 1, right? That's not larger than 1, even though I'm raising it to 400.9. And if I put in S naught of 1, I'm going to be raising something to the power of 400.9, but the thing I'm going to be raising it to is not going to be 1. It's going to be something close to 1. So it's still not necessarily going to be a number that, it's going to be a number less than 1. That's what I'm going to wind up getting. Okay. Actually, it's going to be, this number is going to be a number less than 1. It's not going to be 1. It's going to be a number less than 1. As t goes on, S naught of t is going to get smaller. And as it gets smaller, I raise it to a power, it's going to be even smaller. So what's going to happen is, I'm going to wind up, so now the reason why I chose 2.93 is because it turns out that for this data set, remember there were 21 people in each group? 21 people in each group. And I have 21 people were exposed, 21 people were unexposed. And I had the log white blood cell counts for each of the 42 people. If I take the 42 log white blood cell counts, and I add them up and divide by 42, what I get is 2.93. That's the mean log white blood cell count. You remember when Eli talked about that conditional margins approach for getting the risk ratio, and you plugged in the overall mean value? That's sort of what you're doing here. You're saying, well, look, I have to plug in something for this other variable. Let's plug in the overall mean value. It's not the only way to do it, but let's plug in the overall mean value. So I'm saying, this is what the formula for the survivor curve looks like for somebody who's in the placebo group who has the average log white blood cell count value. So suppose I want to do it for somebody who's in the treatment group. I want to get the survivor curve for somebody who's in the treatment group. How would any of this change? What would change? Well, instead of putting a 1 over here, I put a what?
0.
A 0. So this would drop out. So I get e to the whatever 1.604 times 2.93. That's like 3 times, I don't know, it's not 400.9. It's something like, it's e to the 6 or something like 2.71 to the 6. It's not 400.9. It's going to be a number less than that. But in any case, I'm going to get a different survivor expression for the people that are in the treatment group. So what the computer typically does is it basically lets you do that. It lets you basically say, I can go from the hazard function to a survivor, and I can plot survivor curves comparing the two groups as long as I decide what values I want to plug in for the predictive variables. And if I'm comparing two groups, treatment and placebo, 1, 0, and I'm controlling for another variable, I might use the average value of the other variable in the formula. So that's what this next sort of, there are 2 slides. 2 slides here. I'm going to go to this next one because I don't want to get into the others because of time. So I'll go back to that later. But anyhow, so here's the formula for the survivor curve. To graph the survivor curve, you have to specify values for the x's. In our case, there were 2 x's, treatment and log white blood cell count. To attain adjusted survival curve, you usually use the overall mean values of the x's being adjusted. That's what you usually use, overall mean value. So, if we wanted to talk about 1 versus 0, and we had several control variables, the formula would be S0 of t, the baseline hazard, raised to the power e to the beta 1 times 1, because that's 1 for one of the 2 exposed groups, and that's 0 for the other. And what am I putting in over here? What's this? See, it says xi, but what is that over the top? Bar. What does that mean? It's the mean. So what I'm doing is, for all of the other variables I want to control for, I'm saying that let's assume I compare exposed with unexposed, and I'm going to assume that both groups are at the overall mean value of the variables I want to control for. That's one way to get 2 survivor curves. That's one way to do it, and that's what a lot of people do, okay, to get their survival curves. Okay. Now, a couple of other things to say about this. Well, one thing to say about this. What if the variable of interest, if the variable was log Whitefoot's count, and you got 42 values, and you take the average log Whitefoot's from 42, you're going to get some number between what it turned out to be 2.93. What if the variable was sex, male versus male, female, and you had 42 values? What are the values? Well, it's your call, but let's say you say it's 1 for females and 0 for males, just so that I don't get into trouble. Or I don't know, 1 for females, 0 for males. I can get into trouble anyway. Okay. So you got 42 0 1s. Okay. What if it turns out that of the 42 people in the data set, 60% of them were females? And I'm going to take the average value of the 1s and 0s. What am I going to get? For X bar, what am I going to put in for X bar? 0.6, right? Isn't that what I'm going to put in? That's the average value. So that's what I would, if I'm using this approach, I'm putting in a 0.6 as my average value of the scores for the males and females. That's not unreasonable to do. So that's one thing I could, in other words, I could use the mean whether I'm dealing with a categorical variable, a binary variable, continuous variable, whatever. How might you complain about that? If you wanted to complain. Well, if you're male, if you're female, you're 1, and if you're male, you're 0. You're making an assumption there. Now, you can get into real trouble. I've gotten into trouble before because there's some people say, well, I'm not either a male or a female. I'm somewhere in between. Okay, this is where I can get into trouble. Get what I'm saying? You know? But in any case, even if I code the thing 1 and 0, see, nobody in that data set was a 0.6. They were either 1 or 0. So the number I'm plugging in this formula is not a real number. Unless I want to argue that maybe there's some people who are, 4.6. Okay. But in any case, that's how people have criticized. People have criticized this approach. So when you have a binary predictive variable, you shouldn't use the overall mean. You should do something else. And there's some other methods, and that's described on this slide that I'm not going to go over. Other methods for dealing with that, so you don't have to use the overall mean value. You can consider the proportion of males and proportion of females and not have to use an overall mean value. So there's a way around that. Okay. So with that, I'm going to stop, because what I haven't done today, and that's what I'll do on Thursday, starting Thursday, is show you how you plot a survivor curve using SAS. But we've talked enough about the Cox model, so we'll do that Thursday. Okay. That's where we're going.